Welcome to Engineering Simplified. In this video, we're going to learn how to calculate resistor circuits step by step, whether they're connected in series, parallel, or a combination of both. Before we start solving circuits, let's take a quick look at what we're going to cover. We'll begin with a quick refresher on Ohm's law, making sure you understand the relationship between voltage, current, and resistance. That foundation will make the rest of the calculations much easier to follow. Next, we'll look at resistors connected in series, where you'll learn how to calculate total resistance and understand how voltage is shared between components. We'll then move on to parallel circuits, where you'll see how current divides between different branches and how to calculate the equivalent resistance of a parallel network. After that, we'll combine everything you've learned to solve mixed circuits containing both series and parallel resistors. We'll work through each calculation one step at a time, explaining every stage just as an engineer would. Finally, we'll finish with a viewer challenge, giving you the chance to solve a circuit on your own before we reveal the full worked solution together. By the end of this video, you'll have the knowledge and confidence to analyze and solve a wide range of resistor circuits from start to finish. Before we start solving resistor circuits, we need to understand the most important equation in electrical engineering, Ohm's law. Ohm's law describes the relationship between voltage, current, and resistance. Once you understand how these three quantities work together, you'll be able to solve almost any basic electrical circuit. The equation is simple. Voltage equals current multiplied by resistance, or V equals I times R. Voltage is measured in volts, current is measured in amperes, often shortened to amps, and resistance is measured in ohms. The great thing about Ohm's law is that if you know any two of these values, you can always calculate the third. A useful way to remember the formulas is with the Ohm's law triangle. Simply cover the value you want to find, and the remaining two values show you which calculation to use. For example, if you need to find current, divide voltage by resistance. If you need to find resistance, divide voltage by current. We'll be using these formulas throughout this tutorial, so if you're not completely comfortable with them yet, don't worry. By the end of this video, you'll be using Ohm's law with confidence. Let's begin applying it to real resistor circuits. Now let's look at the simplest type of resistor circuit, a series circuit. A series circuit is easy to recognize because all the components are connected one after another, forming a single continuous path. That means the current has only one route it can take. Starting at the positive terminal of the power supply, the current flows through R1, then R2, then R3, before returning to the negative terminal. Because there's only one path, the same current flows through every resistor in the circuit. It doesn't matter whether the resistor is 220 ohms, 330 ohms, or 470 ohms. The current is identical through all three. This is one of the most important rules of series circuits, and you'll use it again and again when solving electrical problems. Another important point is that every resistor adds more opposition to the flow of current. As you connect more resistors in series, the total resistance increases, making it harder for current to flow. In the next slide, we'll learn how to calculate that total resistance using a very simple formula. Now that you know what a series circuit looks like, let's learn the 4 rules you'll use every time you solve one. Rule number 1. The total resistance is simply the sum of all the individual resistors. If you have 3 resistors connected in series, you just add their values together. Rule number 2. The current is the same through every resistor. Since there's only one path for the current to flow, it can't split or take an alternative route. Every component carries exactly the same current. Rule number 3. The voltage is divided across the resistors. Each resistor uses a portion of the supply voltage, and the size of that voltage drop depends on the value of the resistor. And finally, rule number 4. If you add together all of the individual voltage drops, they will always equal the original supply voltage. This is a useful way of checking that your calculations are correct. These 4 simple rules are the foundation of every series circuit calculation. In the next few slides, we'll apply each of these rules step by calculating the total resistance, the current flowing through the circuit, and the voltage drop across every resistor. Now it's time to put everything we've learned into practice. We'll start by calculating the total resistance. Since these resistors are connected in series, we simply add their values together. 220 ohms plus 330 ohms plus 470 ohms gives us a total resistance of 1020 ohms. Now that we know the total resistance, we can use Ohm's law to calculate the total current flowing through the circuit. We divide the supply voltage of 24 volts by the total resistance of 1020 ohms, giving a current of 0.02353 amps, or 23.53 milliamps. Remember, because this is a series circuit, that same current flows through every resistor. Next, we calculate the voltage drop across each resistor using the formula voltage equals current multiplied by resistance. That gives us 5.18 volts across R1, 7.77 volts across R2, and 11.06 volts across R3. As a final check, we add all three voltage drops together. The result is approximately 24 volts, which matches the supply voltage. That confirms our calculations are correct. We've successfully analyzed our first series circuit, and now you're ready to move on to parallel circuits, where the rules are quite different. Before we move on to parallel circuits, let's take a moment to recap what we've learned about series circuits. The first rule is that the total resistance is simply the sum of all the resistors connected in series. The second rule is that the current is the same through every resistor, because there is only one path for it to follow. The third rule is that the supply voltage is shared between the resistors. Each resistor has its own voltage drop, and the size of that voltage drop depends on the resistor's value. Finally, when we add together all of those individual voltage drops, they equal the original supply voltage. This gives us a simple way to check that our calculations are correct. These four rules are all you need to solve any series resistor circuit. Now that you've mastered series circuits, it's time to move on to parallel circuits, where the behavior of current and voltage changes completely. Now that you understand how series circuits work, let's look at where you'll find them in the real world. One common example is a flashlight, where batteries are often connected in series to increase the supply voltage and provide more power. Another example is older-style string lights. Because all the bulbs are connected in series, if one bulb fails, the circuit is broken and the entire string goes out. You'll also find series connections inside many automotive and electronic circuits, where components are arranged to control voltage levels or limit current. And in sensor and measuring circuits, resistors connected in series are often used to create voltage divider circuits, allowing engineers to produce precise voltages for electronic devices. The key things to remember are simple. Adding more resistors in series increases the total resistance. The same current flows through every component. The supply voltage is shared between the resistors. And as a final check, the sum of all the voltage drops should always equal the supply voltage. Once you've mastered these four rules, you'll be able to solve any series resistor circuit with confidence. Next, we'll move on to parallel circuits, where you'll discover that the behavior of current and voltage is completely different. You've now learned the rules for solving series circuits, so let's see if you can apply them yourself. Take a look at the circuit on the screen and imagine you're solving it without any help. Your task is to calculate the total resistance, the total current, and the voltage drop across each resistor. Remember the process we've just learned. First, add all of the resistor values together to find the total resistance. Next, use Ohm's law to calculate the total current flowing through the circuit. Then, calculate the voltage drop across each resistor by multiplying the current by the resistance of that resistor. Finally, check your answer by adding all of the individual voltage drops together. If your calculations are correct, they should equal the 24-volt supply. Don't worry if you're not completely confident yet. Pause the video now, take a few minutes to work through the problem, and see how many of the answers you can calculate on your own. When you're ready, continue the video and we'll solve it together, step by step. Let's compare your answers with the worked solution and see how you got on. The first step was to calculate the total resistance. Because this is a series circuit, we simply add all three resistor values together. 150 ohms plus 270 ohms plus 360 ohms gives a total resistance of 780 ohms. Next, we use Ohm's law to calculate the total current. We divide the 24-volt supply by the 780 ohm total resistance, giving a current of 0.03077 amps, or 30.77 milliamps. Since this is a series circuit, that exact same current flows through every resistor. Now we calculate the voltage drop across each resistor by multiplying the current by the resistance. Across R1, the voltage drop is 4.62 volts. Across R2, it's 8.31 volts. And across R3, it's 11.08 volts. As always, we finish by checking our work. When we add all three voltage drops together, we get 23.99 volts, which is effectively 24 volts once we allow for rounding during the calculations. That tells us our solution is correct. If you got close to these answers, you're well on your way to mastering series circuits. If not, don't worry. The more examples you work through, the more natural this process becomes. Now it's time to move on to parallel circuits, where you'll discover that the calculation method changes completely. Congratulations! You've now completed stage 2 and learned how to solve series resistor circuits from start to finish. Let's quickly recap the key ideas. In a series circuit, the total resistance is found by simply adding all of the resistor values together. Because there is only one path for the current to flow, the same current passes through every resistor in the circuit. The supply voltage is then shared between the resistors, with each resistor producing its own voltage drop. And finally, if you add together all of those individual voltage drops, they should equal the original supply voltage. That's one of the best ways to check that your calculations are correct. These might seem like simple rules, but they're used every day by electrical and electronic engineers when designing and troubleshooting real systems. Once you understand series circuits, you have a solid foundation for analyzing much more complex networks. In the next stage, we're going to introduce parallel circuits. You'll see that while the components may look similar, the behavior of the circuit is completely different. Instead of the current staying the same, you'll learn how it splits into different branches, while the voltage remains the same across every branch. Let's move on and discover how parallel resistor circuits work. Now that you've mastered series circuits, it's time to look at another very common type of circuit: parallel circuits. At first glance, they look quite different, but once you understand one simple idea, everything else starts to make sense. In a parallel circuit, every resistor is connected across the same two electrical points. That means the voltage across each branch is exactly the same as the supply voltage. In this example, the supply is 24 volts, so R1, R2, and R3 all have 24 volts across them. Unlike a series circuit, the current doesn't stay the same. Instead, when the current reaches the junction, it splits into separate branches. Each branch carries its own current, and the amount of current depends on the resistance in that branch. Notice what happens here. The 120 ohm resistor carries the largest current because it offers the least resistance. The 240 ohm resistor carries less current, and the 480 ohm resistor, which has the highest resistance, carries the smallest current. Finally, all of those branch currents combine again before returning to the power supply, so the total current is simply the sum of the currents flowing through each branch. One more important point to remember is the formula shown at the bottom of the slide. Unlike series circuits, you cannot simply add the resistor values together. Parallel circuits use a different equation, which we'll learn step by step over the next few slides. By the end of this stage, you'll understand exactly why that formula works and how to use it with confidence. Now let's solve our parallel circuit and see how the calculations differ from a series circuit. The first thing to remember is that every resistor has the full supply voltage across it. Since our supply is 24 volts, each branch also has 24 volts across it. Now let's calculate the total resistance. Unlike a series circuit, we don't add the resistor values together. Instead, we add the reciprocals of each resistance. So we calculate 1 divided by 120 plus 1 divided by 240 plus 1 divided by 480. Adding those values together gives 0.01458. To find the total resistance, we take the reciprocal of that answer. So 1 divided by 0.01458 gives a total resistance of approximately 68.6 ohms. Notice something interesting. The total resistance is actually smaller than the smallest individual resistor, which was 120 ohms. That's a unique characteristic of parallel circuits and a useful way to check if your answer is reasonable. Now let's calculate the current flowing through each branch. Because every resistor has 24 volts across it, we can simply use Ohm's law for each branch individually. For R1, the current is 24 divided by 120, giving 0.200 amps. For R2, it's 24 divided by 240, giving 0.100 amps. And for R3, it's 24 divided by 480, giving 0.050 amps. Finally, we verify our answer by adding all three branch currents together. 0.200 plus 0.100 plus 0.050 equals 0.350 amps, which is the total current supplied by the source. That's another important rule of parallel circuits. The total current is always the sum of the currents flowing in each branch. You've now seen how voltage, current, and resistance behave very differently in a parallel circuit compared with a series circuit. And these are the principles we'll use when we start solving mixed circuits. Let's work through one more parallel circuit to reinforce the method. This time, the resistor values and supply voltage are different, but the process is exactly the same. The first thing to remember is that every branch has the full supply voltage across it. Since the supply is 18 volts, each of these three resistors also has 18 volts across it. Now let's calculate the total resistance. We start by adding the reciprocals of each resistor. That's 1 over 60 plus 1 over 90 plus 1 over 180. Adding those three values together gives 0.03333. Taking the reciprocal of that answer gives us a total resistance of 30 ohms. Notice again that the total resistance is less than the smallest resistor, which in this circuit is 60 ohms. If your answer had been larger than 60 ohms, you would immediately know that something had gone wrong. Next, let's calculate the current flowing through each branch. Using Ohm's law, the current through R1 is 18 divided by 60, which equals 0.300 amps. For R2, it's 18 divided by 90, giving 0.200 amps. And for R3, 18 divided by 180 gives 0.100 amps. Finally, we can find the total current in two different ways. We can either add the branch currents together, 0.300 plus 0.200 plus 0.100 equals 0.600 amps, or we can use Ohm's law with the total resistance. 18 volts divided by 30 ohms also equals 0.600 amps. Since both methods give exactly the same answer, we know our calculations are correct. By solving two different examples, you've seen that although the numbers change, the method never does. Once you understand the process, you can apply it to any parallel resistor circuit with confidence. Now it's your turn. Take a look at the circuit on the screen and see if you can solve it without looking ahead to the answers. Using everything you've learned so far, I'd like you to calculate 5 values. First, find the total resistance of the circuit. Next, calculate the current flowing through R1. Then, do the same for R2 and R3. Finally, calculate the total current supplied by the power source. Before you start, remember the 3 key rules for parallel circuits. Every branch has the same voltage across it. The current splits between the branches depending on the resistance of each branch. And to find the total resistance, you must use the parallel resistance formula. Don't just add the resistor values together like we did in a series circuit. Take your time, pause the video if you need to, and work through each step carefully. If you can solve this circuit on your own, you're building exactly the skills that electrical engineers use every day. Once you've finished, continue to the next slide and we'll compare your answers with the full worked solution, step by step. Let's see how you got on. The first question was to calculate the total resistance of the parallel network. Using the reciprocal formula, the answer is 68.6 ohms. Next, we found the current flowing through each branch. Since every resistor has the full 24 volts across it, we simply applied Ohm's law to each resistor individually. For R1, the current is 0.200 amps. For R2, it's 0.100 amps. And for R3, it's 0.050 amps. Finally, to find the total current supplied by the source, we simply add the 3 branch currents together. 0.200 plus 0.100 plus 0.050 equals 0.350 amps. If these were your answers, congratulations, You've understood the key principles of parallel circuits. If you made a mistake, don't be discouraged. Go back through the calculations one step at a time and check where things started to differ. That's one of the best ways to build confidence with electrical calculations. The important things to remember are these. Every branch in a parallel circuit has the same voltage across it. The current divides between the branches according to each branch's resistance. The total current is the sum of all the branch currents, and the total resistance is always less than the smallest resistor in the network. Now that you've mastered both series circuits and parallel circuits, we're ready for the final stage of this tutorial, mixed circuits, where we'll combine both methods to solve more realistic engineering problems. Before we move on to mixed circuits, let's quickly compare the two circuit types we've learned. On the left are series circuits. In a series circuit, all the resistors are connected end to end, so there is only one path for current to flow. That means the current is the same through every resistor. The total resistance is simply the sum of all the resistor values, and the supply voltage is shared or divided across the resistors. Now let's compare that with parallel circuits. In a parallel circuit, every resistor is connected across the same 2 points. Because of this, every branch has the same voltage across it. The current divides between the branches depending on the resistance of each branch. The total current is the sum of all the branch currents, and the total resistance is always less than the smallest individual resistor in the network. So remember these 4 key differences. Series circuits. Current stays the same, voltage divides. Parallel circuits. Voltage stays the same, current divides. If you can remember those 4 rules, you'll be able to solve the vast majority of resistor circuit problems with confidence. In the next section, we'll combine everything we've learned and start solving mixed series and parallel circuits, just like the ones you'll see in real engineering applications. Now it's time to put everything together. So far, we've learned how to solve series circuits and parallel circuits separately. But in the real world, most electrical circuits are actually a combination of both. These are called mixed circuits. The key to solving them is to break the circuit into smaller sections. First, identify any resistors that are connected in parallel and replace them with a single equivalent resistance. Then, continue simplifying the circuit until only one equivalent resistance remains. Looking at this example, R2 and R3 are connected across the same 2 points, so they form a parallel branch. Meanwhile, R4 and R5 are connected end to end, with no branching between them, so they are in series. Finally, R1 is also in series with the rest of the circuit. By simplifying one section at a time, what looks like a complicated circuit becomes much easier to solve. Your challenge is to calculate the total resistance and the total current supplied by the 24-volt DC source. Let's work through it together, step by step. Before we start calculating, the most important step is to understand how the circuit is connected. If you can identify which resistors are in series and which are in parallel, the calculations become much easier. Let's start by looking at the middle of the circuit. Notice that R2 and R3 are connected between exactly the same 2 junctions. Because they share the same top node and the same bottom node, they are connected in parallel. Next, look over to the right. R4 and R5 are connected end to end with no branching between them. That means R4 and R5 are in series, so later we'll be able to combine them into a single equivalent resistance. Finally, R1 sits at the beginning of the circuit, in series with the rest of the network. So we've successfully broken the circuit into 3 simple sections. R2 and R3 are in parallel. R4 and R5 are in series. R1 is in series with both of those sections. This is the key idea when solving mixed circuits. Always identify the series and parallel sections first, simplify them one at a time, and the entire circuit becomes much easier to analyze. Next, we'll calculate the equivalent resistance of the parallel branch formed by R2 and R3. Now that we've identified R2 and R3 as being in parallel, the next step is to combine them into a single equivalent resistor. Whenever 2 resistors are connected across the same 2 points, we use the parallel resistance formula. The formula is 1 over the equivalent resistance equals 1 over the first resistor plus 1 over the second resistor. Or mathematically, 1 divided by R equivalent equals 1 divided by R2 plus 1 divided by R3. This formula gives us one new resistor that behaves exactly the same as the two original resistors. Once we've found that equivalent resistance, we can replace R2 and R3 with a single resistor, making the rest of the circuit much simpler to analyze. Remember, this formula is only used because R2 and R3 share the same two connection points, which means they are connected in parallel. In the next step, we'll substitute the actual resistor values into the formula and calculate the equivalent resistance of this parallel branch. Now let's substitute the resistor values into our parallel resistance formula. We've already identified that R2 is 6 ohms and R3 is 12 ohms. Starting with the formula, 1 over R23 equals 1 over R2 plus 1 over R3. Now replace the resistor symbols with their actual values. That gives us 1 over R23 equals 1 over 6 plus 1 over 12. At this stage, we're not solving the equation yet. We're simply inserting the known resistor values into the formula. Notice that we're adding two fractions. Before we can do that, they must have the same denominator, or bottom number. So our next step will be to convert these fractions into a common denominator, making them easy to add together. Once we've done that, we'll be able to calculate the equivalent resistance of the parallel branch and continue simplifying the rest of the circuit. Now we're ready to add the fractions together. From the previous step, we had 1 over R23 equals 1 over 6 plus 1 over 12. Before we can add these fractions, they must have the same denominator. The least common denominator of 6 and 12 is 12. So we convert 1 over 6 into an equivalent fraction with a denominator of 12. To do that, we multiply both the top and bottom by 2. That gives us 2 over 12. Now both fractions have the same denominator, so our equation becomes 1 over R23 equals 2 over 12 plus 1 over 12. Adding the numerators gives 1 over R23 equals 3 over 12. We've now combined the two parallel resistor fractions into a single fraction. We're almost finished. In the next step, we'll invert this fraction to calculate the equivalent resistance of R2 and R3, replacing the two parallel resistors with one equivalent resistor. We've almost finished finding the equivalent resistance of the parallel branch. In the previous step, we found that 1 over R23 equals 3 over 12. But remember, this isn't the value of R23 itself. It's the reciprocal, or 1 over R23. To find the actual resistance, we simply invert the fraction. That means we flip the numerator and the denominator. So instead of 3 over 12, we get 12 over 3. 12 divided by 3 equals 4 ohms. So our equivalent resistance is R23 equals 4 ohms. This means the two parallel resistors, R2 and R3, can now be replaced with a single 4 ohm resistor that behaves exactly the same as the original parallel combination. This is a major milestone because our mixed circuit has just become much simpler. In the next step, we'll redraw the circuit using this new 4 ohm equivalent resistor and continue reducing the circuit until we find the total resistance. We've successfully found the equivalent resistance of the parallel branch. R2 and R3 together are equal to a single resistor of 4 ohms. Now we can redraw the circuit using this new equivalent resistor. Notice what's happened. The two resistors in parallel have disappeared and have been replaced by just one 4 ohm resistor called R23. This new circuit behaves exactly the same as the original one. We haven't changed how the circuit works, we've simply made it much easier to analyze. Now look carefully at the simplified circuit. Notice that R4 and R5 are connected end to end, with no junction or branching point between them. That means the same current must flow through both resistors. Whenever that happens, the resistors are connected in series. And for series resistors, the calculation is simple. We just add their resistance values together. So, R45 equals R4 plus R5. That's 8 ohms plus 10 ohms, which gives us 18 ohms. So we can now replace R4 and R5 with a single equivalent resistor called R45 with a value of 18 ohms. Our circuit is becoming much simpler. Instead of 5 separate resistors, we've now reduced the circuit to just 3 equivalent resistances. In the next step, we'll notice that R23 and R45 are now connected in parallel, allowing us to simplify the circuit even further. One branch has an equivalent resistance of 4 ohms, and the other has an equivalent resistance of 18 ohms. Since these two resistors are connected across the same 2 points, they are in parallel. So once again, we'll use the parallel resistance formula. 1 over R sub P equals 1 over R23 plus 1 over R45. Now substitute the values. 1 over R sub P equals 1 over 4 plus 1 over 18. To add these fractions, we need a common denominator. The lowest common denominator of 4 and 18 is 36. So 1/4 becomes 9 over 36, and 1/18 becomes 2 over 36. Adding them together gives us 11 over 36. Remember, this is still 1 over the equivalent resistance. So now we invert the fraction. R sub P equals 36 divided by 11, which equals approximately 3.27 ohms. We've now replaced both parallel branches with a single equivalent resistance of 3.27 ohms. The circuit is almost completely simplified. In the next step, we'll add this resistance in series with R1 to calculate the total resistance of the entire circuit. We've now combined the two parallel branches into a single equivalent resistance of 3.27 ohms. That leaves us with a very simple circuit containing just 2 resistors in series. A 4 ohm resistor and our equivalent resistance of 3.27 ohms. Since they're in series, we simply add them together. The total resistance is R sub T equals R1 plus R sub P. Substituting the values gives us R sub T equals 4 ohms plus 3.27 ohms, which equals 7.27 ohms. And that's it. We've reduced a circuit that originally contained 5 resistors with both series and parallel sections into a single equivalent resistance of 7.27 ohms. This is the value the 24-volt power supply sees. Finding the total resistance is always the first major step when solving a mixed circuit. Now that we know the total resistance, we're ready to use Ohm's law to calculate the total current supplied by the source in the next step. We've now simplified the entire mixed circuit into a single series circuit. We already know that the total resistance is 7.27 ohms. Now we can use Ohm's law to calculate the total current supplied by the 24-volt DC source. The formula is current equals voltage divided by resistance, or I sub T equals V divided by R sub T. Now substitute the values. The voltage is 24 volts and the total resistance is 7.27 ohms. So, I sub T equals 24 divided by 7.27. This gives us a total current of approximately 3.30 amps. And that's the current flowing from the power supply into the circuit. Once we've found the total current, we can work backwards through the circuit to calculate the current and voltage at every resistor if required. This step-by-step approach is exactly how engineers solve even very complex electrical circuits. In the next example, we'll tackle another mixed circuit with different resistor values so you can practice the same method again. Now it's your turn to solve a mixed circuit. This example uses the same step-by-step method we've just followed, but the resistor values and supply voltage are different. Your task is to calculate 2 values, the total resistance of the circuit and the total current supplied by the 18-volt source. Start by examining the circuit carefully before doing any calculations. First, look for resistors that are connected in series. Here, R4 and R5 are connected end-to-end, so those 2 resistors can be added together first. Next, look at the remaining branches connected between the same top and bottom nodes. Those equivalent branches will need to be combined using the parallel resistance formula. Continue simplifying the circuit one section at a time until only one equivalent resistance remains. Once you have the total resistance, use Ohm's law. Current equals voltage divided by resistance. Pause the video now and work through the calculation carefully. Try to redraw the circuit after every simplification. That makes it much easier to see what should be combined next and helps prevent mistakes. When you're ready, continue to the next slide and we'll go through the complete solution together. Let's work through the solution together using exactly the same method we've been using throughout this course. Step 1 is to simplify the obvious series section. R4 and R5 are connected end-to-end, so we add them together. R45 equals 6 ohms plus 12 ohms, which gives us 18 ohms. Now redraw the circuit with R45 replacing R4 and R5. Next, look for any parallel branches. We now have R2, R3 and R45 all connected across the same two nodes, so they're in parallel. Using the parallel resistance formula gives an equivalent resistance of approximately 2.32 ohms. Redraw the circuit again. Now only two resistors remain in series. R1 is 3 ohms and the equivalent parallel resistance is 2.32 ohms. Adding them together gives the total resistance. R sub T equals 3 plus 2.32, which equals 5.32 ohms. Finally, we use Ohm's law to calculate the total current. Current equals voltage divided by resistance. So, I sub T equals 18 volts divided by 5.32 ohms, which gives us approximately 3.38 amps. So our final answers are a total resistance of 5.32 ohms and a total current of 3.38 amps. The important thing isn't just getting the correct answer, it's following a logical process. Simplify one section at a time, redraw the circuit after each step, and even the most complex resistor networks become straightforward to solve. Congratulations! You've now completed the Engineering Simplified Resistor Calculations series. You've learned how to identify series and parallel resistor networks, simplify mixed circuits, calculate equivalent resistance, apply Ohm's law, and verify your answers with confidence. Most importantly, you've learned the engineering process. Rather than trying to solve a complex circuit all at once, you now know how to break it down into smaller, simpler steps until the solution becomes clear. This is exactly the same logical approach used by engineers every day when solving electrical design problems. If you enjoyed this video, please give it a like and subscribe to Engineering Simplified. Every like, subscribe and comment really helps the channel grow and allows us to keep creating free engineering content for everyone. If there's an engineering topic you'd like us to explain, let us know in the comments below. Thanks for watching, and I'll see you in the next Engineering Simplified video.